Hi class, welcome back. Today we're going to discuss 2.5, and this section we are specifically talking about implicit differentiation, and the objectives to cover are distinguish between functions written in implicit form and explicit form, and also use implicit differentiation to find the derivative of a function. Alright, so what does it mean implicit versus explicit? So explicit is what we've been doing all along. So we've been doing this when we had the equation y solved for. So that's all it means. If you have y solved for, that means we had an explicit function. It was explicitly defined, right? So in terms of y. So y was the unknown, the function, and it was explicitly written as a function of x. There was no y's here, it was only here, right? So y was solved for. That's the best way you can think of. If y is not solved for, then that's known as implicit. So the function y equals 1 over x is defined and implicit if it is in this form. So if you notice, these two functions are the same. These two functions are the same, but in this case, this is known as implicit equation versus this one is explicit. So here's a perfect example. This is implicit form because y is not solved for. This is explicit because y is solved for. So they're the same equation. They have the same solution, except that they're written in different forms, right? And so in our class, we were dealing always with finding derivatives for functions that were explicitly defined, right? The explicit form. So for example here, if we ask to find the derivative of this equation, all we had to do is rewrite it in power form and then apply the power rule, which means bring down, copy paste the power, -1, multiply by x, and then subtract 1 from the power. And that gives us -1 over x squared, right? By moving the x to the denominator to change the power sign. All right, very good. So now, there's a benefit and there's a disadvantage of using implicit differentiation. So you guys will see we're gonna do a few problems where we're gonna differentiate implicitly. Now we have to open our minds in a different approach, but other than that, it's very similar to what we've done before. Now implicit differentiation is very good whenever it's almost impossible to solve for y, and requires maybe a very hard technique of algebra to be able to get there. So what implicit differentiation is allowing us to do is we don't actually need to solve for y to be able to find y prime, as you guys will see in a second. All right, so real quick here, let's review a few things. In this example, I'm asking you guys to find the derivative of x cubed. Now, if you guys remember all along, the function was taking the derivative in respect to a variable. If you notice, that variable matches that variable. So if this is the variable that's being that we're taking the derivative in respect to, that means that this is treated as a variable, right? And so when we do the derivative of this, then what we're pretty much doing is doing derivative as we done before. The derivative of this will be take the power of the x, multiply it by x, and then subtract 1 from the power. And so that gives us 3x squared. All right, perfect, right? So that was it, right? That's what we've been doing before. So let's move on to the next example here. Now if you notice, this variable, this has a y function, this has a y variable, and this has an x variable. Well, in this example, what we're assuming here is that y is a function of x, meaning we cannot approach it the same way. Here, in this example, we're going to treat y as a function. Now, do we know how this y function looks like? No, we don't. Does it matter? No, it doesn't matter. So the way we're going to do this is we're going to use the approach of a chain rule. Do you guys remember that than when we used chain rule was because we had a function inside another function, right? So if you guys need to use parentheses here to visualize it, I can do that for you, right? Y is the function. Why do we know why are we treating y as a function? Because of this right here. Because x is the independent variable, and that means that y has to be the dependent variable. It depends on x. It's a function of x. All right. So treat y as a function that you don't know. So here we go. Take the derivative of this. So what are we going to use? We're going to use chain rule. So how do we do chain rule? Well, in this case, it's going to be the general power rule. So let's try that. The derivative of this says that we take the derivative of the outside function, which is the power form. So it will be 3. Leave the inside function as it is. Take away 1 from the power. And then multiply by the derivative of the inside. Right? Isn't that what chain rule says? Now we're going to fix this. We're just going to write it of this form. Right? Because y prime means dy over dx. So there you go, right? Was the last step needed? No, it wasn't, but hopefully it kind of makes sense. All right. So let's move on to the next example. Let's take the derivative of this. If you guys notice, again, let's note that this is the derivative in respect to x. So x is the independent variable. Y is the dependent variable. So y depends on x. That's the assumption that we have. So we're going to go ahead and take the derivative. The derivative of x will just be, when you do with this one, you're going to treat it the same way that we've done it before. The derivative of x is going to be 1. Followed by plus, so I'm going to write myself a note. Y is a function of x. So when I do the derivative of this, I'm going to treat y as a function. So I'm going to have 3 times the derivative of the function. I don't know what the function of y is because I don't know what y is. So I have to leave it like this. Does it bother you that we have to leave it like this? Probably, right? Because we're not getting something concrete. But that's fine. We got to get used to that, right? It's fine to leave it like that. Let's try another one. So in this example, again, we have to recognize in what respect are you dealing the problem with. So we're doing this in respect to x. So again, let's write ourselves a note. Y is a function of x. So now this is interesting because what do we have here? We can see here that x is a function, right? By itself is a function, right? But then we also have this as a function. So I'm not sure if you guys are seeing this, but the rule says when you multiply two functions, then you have to do product rule. So here we're gonna do product rule. So I'm gonna start by doing x times the derivative of the second one plus the derivative of the first one times the second one, right? Do we agree that that's product rule? Let's see what happens. So for the first part, x is just x. The derivative of y squared, we have to use general power rule, in other words, chain rule, right? So let's try that. It will be multiply by the power, multiply by the inside function, subtract 1 from the power, so that becomes a 1, and then multiply by the derivative of the inside, right? Chain rule, because remember y is a function of x. Followed by the derivative of x is 1 times y squared. And there you go. So now can we clean this up? We can say that this is 2 times x times y dy dx plus 1 times y squared. And there you go. So that's the derivative. So do you guys see the difference between both of them? Do you guys see why we had to use product rule and why we didn't have to use product rule on part C? If you guys notice, please note this. Then this is in this case, x was by itself, right? This was the sum of two functions. Here, this is treated as a product of two functions. So there you go. All right, so we're gonna do a few more, but we have some guidelines we can follow. So when you differentiate implicit functions, right, then we are basically doing the following. Step number 1, differentiate both sides of the equation with respect to x. So treat x as the independent variable and y as the dependent. Number 2, then collect all terms involving dy dx on the left side of the equation and move the other terms to the right side of the equation, as we see in the next. Then factor dy dx out of the left side of the equation and then solve for dy dx. So here we go. Here's a perfect example. This is a beautiful example because it's going to show us everything. Now you guys will see here that that there is half of the work is based on the subject that we are discussing, which is calculus, but half of it has to do with algebra. In fact, in some points it becomes 3/4 of the work is algebra, and then 1/4 of it is calculus. So what we're going to do here is we're given this equation right here: y cubed plus y squared minus 5y minus x squared equals -4. And they're asking me to find dy dx. Now, just because of the structure and the notation, this is suggesting that x is the independent variable and y is the dependent variable, which means that y, let's write this out, y is a function of x. So x is just x the normal way, but y is a function. So let's go ahead and find dy dx. To do that, what we're going to do is we need to find the derivative of y. So what we're going to do is sort of kind of like the concept of algebra. We're going to take the derivative of the left side, but whatever you do on one side, you have to do it to the right side to maintain balance on the equation. So you guys notice here on blue, I took the derivative of the left side equals to the derivative of the right side. And then because of the sum and difference rule of derivatives, it allows me to take the derivative of every term independently of each other. So I have this term, I'll take the derivative of this term, take the derivative of that term, take the derivative of that term. So what you guys notice, that's what I did. So, and then I still have the right side, right? Once I did that, I can do that one term at a time. Take the derivative of this. Now I remind you guys that y is a function. So you have a function inside another function of a power of 3. So you have the general power rule here. In other words, the chain rule. So take the power 3, multiply by the inside function, which is y, subtract 1 from the power, and then multiply by the derivative of the inside. That was chain rule for this. Apply chain rule here again because y is a function that we don't know, right? So take the power of 2, multiply by the inside function, which is y, take away 1 from the power of 2, which becomes a 1, and then multiply everything by the derivative of the inside, which is y prime. Followed by the minus. The factor of 5 carries over. The derivative of y happens to be just y prime. No need to do power rule because that's just a function times a constant. Minus x squared, and this is treated the normal, right? Normal way. So this would just be multiplied 2 by x minus 1. So that would be 1 there. Equals to the derivative of a constant is 0. So there you go. This line right here happened to be the only line that has to do with calculus. Everything else is going to be algebra. So if you guys pointed out, if you guys notice, there's 3 terms, 1, 2, and 3 terms that contain the factor of y prime. And y prime is actually what we're looking for, right? Y prime is dy dx. So if that's what we're looking for, and that's what then that means that's what we need to solve for. So that means every term that does not have a y prime needs to be moved to the other side, to the right side. So I'm going to add 2x on both sides. Now you see it there. And along these 3 terms, because all three have a common factor of y prime, I will factor it out, leaving behind 3y squared plus 2y minus 5. Now notice that this is I factor it out, and now I can go ahead and divide both sides by that term. So I can bring here and then divide both sides by 3y squared plus 2y minus 5. 3y squared plus 2y minus 5. And this cancels, and now we have y prime, which is dy dx, equals to 2x all over 3y squared plus 2y minus 5. And there you go. We have found dy dx implicitly, right? Now, if you guys notice, we didn't have to solve for y. We didn't actually have to solve for y. Now, think about this for a second. Because if you guys think about this will make sense more. Why are we doing this? Notice how hard would it be to solve for y here, right? It would be very hard even for me to do that, right? It will be very, very hard for us to do that. So and we didn't actually have to solve for y in order for us to find the derivative of y. So what we just found is the slope formula for this graph right here. So this graph right here is the equation that they gave us. Now we have found the formula of the slope for every single point on this graph. And so it can be found with this. Now y is not a function, because we can see here, if you guys notice, y is not a function because y does not satisfy the function, does not pass the function test, right? Which means they cannot touch more than 1 point and the vertical line test. Okay, so I hope that you guys find this helpful. Why we're doing this? I mean, now this is gonna open. This is providing us another tool that we can use to find the rate of change of anything, of any function, of any situation, without actually having to solve for y. All right. So we're gonna move on to the next part here. You guys can try a few more examples here and there, and I'm gonna try example number 5. So in example number 5, they're asking us to find the slope of the graph implicitly, meaning we don't have to solve for y. Then determine the slope of the graph of this equation at the given point 3, 1. So we don't actually need to solve for y in here to find the derivative. We can just do it directly by doing implicit differentiation. So here we go. Let's look at the equation. So the black letters represents the original equation. We're going to take the derivative on the left side, so we have to take the derivative on the right side to maintain the same value of the equation, right? Now on the left side, this is going to create a lot of we're going to have to define which rule we're going to have to use. So if you notice, let's think about this. We're assuming that y is a function of x. So y is a function of x that we don't know, right? So here we go. So 3 is a constant. Then we have x squared plus y squared squared. So if you notice that we actually have a function inside a function, right? So if you're thinking already, hey, in the bigger picture, we're gonna have to use the general power rule, in other words, chain rule. So yes, we're gonna have to do that. But what about the right side? The right side, we actually have a product of two functions. So x is the function of x, and then y is a function that we don't know what the function represents, right? It's in terms of x. We know that, but we know that this is a product, so we're gonna have to use the product rule. So on the left side, let's begin. So if you notice, if you follow here, What we're going to do first is we're going to apply the derivative of the outside. That means copy and paste the power, multiply by the inside function, and then take away 1 from the power, so that's 2 minus 1, that's 1. And then multiply by derivative of the inside. And that's what I did with this mark here. What about the right side? So what I did here is I let the 100 by itself outside, right? I just moved it outside. It's just a constant, so I can do that. And I did the product rule for this. So the derivative of x, the first one, times the second one, plus the first function times the derivative of the second one, right? That's the plan. So here on the left side I use chain rule, on the right side I use product rule. It is what it is, right? It is what you need to do. So you gotta figure out which rule you need to do. That's sometimes the name of the game here with derivatives, is knowing which rule to use. So 3 times 2 will give us 6. This stays the same, and then now we can take the derivative of this. The derivative of x squared happens to be 2x. Plus the derivative of y squared, we're going to treat y as a function, so we have to use a chain rule. So bring down the 2, leave the inside as it is, and multiply by the derivative of the inside. Right? So that's why this flows out in the process. For this part, we have the 100. The derivative of x is 1, y is y, plus x is x. The derivative of y, well, we don't know what y is, so we're going to leave it as y prime. And we're going to distribute the 100 on the right side, and on the left side we're going to do the same thing. We're going to distribute this whole thing to both terms. Why? Because at this point, and let me put this in blue. Let me put this in blue. We are trying to solve for y prime. Right? We're trying to solve for y prime. So I need to have all the y primes on one side. So maybe I'll keep the y primes in a different color so it calls your attention. Alright, so here we go. Let's continue with this. So I distribute this, and at this point we're pretty much done with calculus, right? Everything that we're going to be doing now doesn't have to do anything with calculus. It's all algebra, right? So that's why I keep telling you guys, review your algebra, right? So at this point, we're going to distribute this. Let me go back over here. We're going to distribute this to the 2x. So 6 times 2x gives you 12x times this. 6 times this times 2y, y prime, multiply the 6 and the 2, gives you 12, followed by the y, followed by the y prime, followed by the product x squared plus y squared. On the right side we have 100 times y, 100 times x y prime, and that's pretty much it. Now what I notice is that my left side and my right side, they all have a factor of 4. So what I'm doing here is I'm sort of dividing the left side by 4 to simplify my values. I'm also doing that on the right side. Whatever I do one side, do it to the other side. So these will simplify, right? Remember that every term will be divided by 4. So that's how we got the 3x. That's how we got the 3y. That's how we got the 25y. And that's how we got the 25x. I'm going to go ahead and write this as y prime. Alright, so our goal is to have all the y primes on one side, but we cannot move them without their term. So what I'm going to do here is I'm adding. I'm going to keep this one here, but I'm going to move this to the other side by getting rid of this one, minus 25x y prime, minus 25x y prime. This will cancel. Do the same thing over here. I'm going to subtract this term out of the way, so negative 3x plus times x squared plus y squared will be subtracted on this side. That will cancel. So what's left behind is these two terms and these two terms on the other side. So that's what we get on the other side. So we can compare them. Minus 25x y prime 3y y prime times x squared plus y squared equals 25y plus or minus 3x times x squared plus y squared. So we agree, we get the same thing. Now notice again, let me put this in a different color. Y prime is part of both terms, right? It's a factor of both terms. So because it is a factor of both terms, that means it is a common factor. If it is a common factor, we can use basic algebra to factor y prime from both terms. What's left behind? Minus 25x plus 3y times the quantity x squared plus y squared equals to the right side. Now because this is a product, right? This is a product. Now we can divide both sides by this whole thing. And I think I'm missing one of the parentheses here. There you go. So I divided both sides by this quantity. And that's how I got it underneath the other side, right? And that's our value. Now that was part of the question. They asked us to determine the derivative of this, but they want us to find the derivative of this at that particular point, 3, 1. So what are we going to do now? So for now, we're going to utilize the fact that they want us to find the slope at a particular point, and that point has a value of x equal to 3 and a y value equal to 1. So I'm going to replace, every time I see a y, replace it with 1. Every time I see an x, replace it with 3. And then simplify it, and that will be automatically my slope. Why? Because that's the derivative. Derivative relates to the slope of the point. So if you do that, then you should be getting 13 over 9. Right. So do you guys see how the algebra is very important in this problem? It's actually where most of the students will get lost. Alright, so one more example. You guys remember that we keep asking you about the tangent line, finding the equation of the tangent line? Well, here's another example. Find the equation of the tangent line to the graph x squared times the quantity x squared plus y squared equals y squared at a particular point, square root of 2 over 2, square root of 2 over 2. So what are we looking for? We're looking for the equation of the tangent line. How does that look like? It always looks like y equals mx plus b because it's a linear equation. So what are we going to do? Find the slope. How do we find the slope? By finding dy over dx. In other words, y prime. So what are we going to do? We don't need to solve for y. We just have to take the derivative on both sides of the equation. The derivative of the left side, derivative of the right side. Now what happens on the left side is that we have to see this as being the product of two functions, x squared times this quantity. So I'm going to do product rule. The derivative of the first one times the second one plus the first one times the derivative of the second one equals times the derivative of the right side. So let's go ahead and execute the derivative. The derivative of x squared is 2x times this function plus x squared. The derivative of this, we just have to do the derivative of this independently, 2x, and the chain rule tells us that we're going to have 2y times y prime, right? Don't forget the y prime. The derivative of this, we're going to have to use also chain rule, 2 times the inside, subtract 1, multiply by the derivative of the inside. And that's how we got those. So if you notice, we have two terms that have a y prime. We need to solve for those two. Now here's an alternative way to do this. We could do the whole hard math to be able to solve for y prime. But an alternative way to do this, since we're only looking for a slope at a particular point, we can also utilize the fact that we already know that x is the square root of 2 over 2 and y is the square root of 2 over 2. So that's actually what I did. I ended up replacing every time I see an x with the square root of 2 over 2. Right, do you guys see that? And then I did the same thing for the y. Every time I see a y, I replace it with square root of 2 over 2. Notice that I still have the y primes. In fact, let me rewrite those in blue. Oopsie. Let me write those in blue. That way they're more they're obvious. We're still going to solve for y prime. But now my assumption is that this will be easier for us to compute. So the inside of this will be 2 times this. What happens with the 2's? They cancel each other out, so we're left with the square root of 2. Inside the brackets, we have the square of the square root of 2 over 2, which becomes 2 over 4. Same thing for this one, 2 over 4, followed by the plus, followed by the plus. Here we have the square of the square root of 2 over 2, which becomes 2 over 4, followed by the bracket. Those two will cancel each other out, the 2 and the 2. The 2 and the 2 will cancel each other out, so we're left with the square root of 2 plus the square root of 2 times y prime. And follow equals to the square root of 2 over times y prime, right? Those two will cancel each other out as well, those two. So you guys see here that these can simplify, right? 1/2, this is the same thing as, well, 2 fourths plus 2 fourths is 4 fourths, which gives you 1, times the square root of 2. Plus, right? And then this is basically 1/2 multiplied by the square root of 2 is square root of 2 over 2. Followed by the plus, 1/2 times the square root of 2 gives you square root of 2 over 2 times y prime. So I did that, I did an extra step in my head, so I hope you guys are able to follow that. I noticed that this was 1/2, so I multiplied that in every term. Then follow the right side, right? Just carry it over. Now this is just going to be the square root of 2. This is just going to be the square root of 2 over 2. I can combine those two by having common denominator. This will need to be a 2 over 2. So this becomes 3 square root of 2 over 2. And then what I did with these two is I subtract that on both sides of the equation. So I subtracted square root of 2 over 2 y prime on both sides of the equation. That's how I got this part over here. And then I noticed they both have a common factor of y prime. Again, let me highlight those. And then I factored it out. In other words, I simplified these two. So by having common denominator, that would become, if you guys want to see this would be 2 over 2. So it becomes 1 square root of 2 over 2 y prime. And let's move on to here. Here we're gonna have we are pretty much almost solved for y prime, except that we have this part right here. So what about if we multiply by the reciprocal of this, meaning if we multiply both sides by 2 over the square root of 2, 2 over the square root of 2. Let me do that on here if you guys can kind of see it. Multiply by 2 square root of 2, 2 square root of 2. What happens here? These will cancel each other out, and so you're left with y prime equals 3. There you go, right? And then so we found y prime. So y prime is 3. That means that the slope is 3. It means the slope is 3. So we're gonna use that into the equation, right? So if you guys go back to the equation, m is 3. So I replace that in here. And then I use the fact that we already know x and y, and I use them here and there to be able to solve for b, as we've done it like 100 times already in this class. So I multiply these two together, and then I subtract it on both sides of the equation, giving us negative 2 square root of 2 over 2. So that means that this is 1 minus 3 gives you negative 2. And then this is going to be b, right? This is going to be equal to b. So that's your b. Now this can be simplified. These will cancel each other out. And so therefore you have b equals negative square root of 2. And that's it. So we found our tangent line. All right. So I hope this is helpful. The key that you guys want to get from this section is when you're dealing with implicit differentiation, means you have an equation that is not solved for y. If you want to find y prime, then you're going to take the derivative on both sides of the equation, and you're going to treat y as a function that you don't know. It's a function of x that you don't know how it looks like. But nonetheless, you're still going to use it, and when you take the derivative of it, you're going to have to use chain rule. Okay. All right, so see you guys in class.